Back in Season 1, you learned a strange and wonderful fact. A modern AI can get smarter on a hard question simply by thinking longer before it answers. Pause, work it through, come back with a better answer. So here is the obvious move, the one almost everyone makes first. If thinking helps, turn the thinking all the way up. Maximum effort every question always. More is better. And that instinct will quietly cost you a fortune, and it will sometimes hand you a worse answer than if you had let the model think less. Because thinking, it turns out, is not a switch. It is a dial. Every notch you turn it costs real money and real time while buying you less and less. This episode is about how to read that dial, when more thinking genuinely helps, when it just burns cash. And a deeper question hiding underneath. When a model shows you it's thinking, is that really what it did? Start with the thing that makes this whole episode matter. For years there was only one way to make an AI better: scale. A bigger model, more training data, more compute, all paid once up front, before anyone ever used it. Then reasoning models opened a completely separate road. You can leave the trained model exactly as it is, and still buy more accuracy at the moment you ask the question, just by letting it generate more thinking before it answers. The standard name for this is test time compute, sometimes inference time compute, and it is a genuinely second axis of scaling. But here is the shape almost nobody tells you, and it changes how you should use it. Accuracy does not climb in a straight line as you add thinking. It climbs roughly with the logarithm of the thinking tokens. In plain terms, to keep improving, you have to keep multiplying the thinking, not just adding to it. 100 thinking tokens to 1,000 might buy a big jump. 1,000 to 10,000, a smaller one. 10,000 to 100,000, smaller still. The curve bends over and flattens. To make this concrete, one early reasoning model on a hard math contest was reported climbing from roughly the mid-70s to the low 80s to the low 90s in percent correct as it was given more and more compute to think at answer time. Those were real gains. But to get each one, the thinking had to be multiplied again, so each step up cost far more than the last. That is one model, on one benchmark, and the exact numbers will date, but the bending shape is the lesson that lasts. So if thinking is a dial, where is the dial? It is not a metaphor. In 2026, the people who build these models put an actual control in your hands. With one major lab's models, you set a reasoning effort, picking from a small ladder of named levels from none, through low, medium, high, on up, and the model spends more or less thinking accordingly. Another lab moved to an adaptive approach, where the model itself decides how hard to think based on the question, while you nudge it with a coarse effort level. Their older method, where you handed it a fixed number of thinking tokens to spend, is now being retired, and will even refuse to run on their newest models. A third lets you set an explicit thinking budget, a hard cap on how many tokens it may think for. The exact names and settings here will absolutely drift. This is a snapshot of a fast-moving moment, so do not memorize the knobs. Memorize the shape underneath them all. Somewhere you or the model are choosing a point on that bending curve, choosing how much to spend. And the whole skill is choosing well, because the dial does not know whether your question is a one-line lookup or a research-grade proof. You do. Now there is not just one way to spend that thinking. There are two fundamentally different shapes, and knowing which to reach for is half the game. The first shape is sequential. This is the one from Season 1, a single long chain of thought where the model works step by step, checks itself, hits a dead end, backs up, and tries another route. One train of thought that corrects itself as it goes. Depth. And a modern reasoning model can even pause that chain mid-thought to call a tool, run a search, do a calculation, then fold the result back in and keep reasoning. The second shape is parallel. Instead of one long attempt, you fire off many independent attempts at the same question, each thinking on its own, and then you pick the best, often by simple majority vote, whichever answer the most attempts agree on. People call that best of many or self-consistency. Depth versus breadth. And they trade off in a useful way. A long sequential chain builds deep, multi-step arguments, but one wrong turn early can poison the whole thing. Many parallel attempts are more robust, since a single bad attempt just gets outvoted, and because they run independently, you can run them all at once and get your answer sooner, even though you spent more total compute. Research suggests the genuinely smart move is to mix the two, with the right mix depending on how hard the question is. A well-chosen strategy can be several times more efficient than blindly sampling more, and in some specific regimes, a smaller model that spends its thinking well can even match a model many times its size. That last claim is regime-specific, not a universal law, but it tells you the lever is real. Here is where the money gets burned and where almost everyone gets it wrong. Remember that bending curve. Past a certain point, more thinking stops helping and it can actually start to hurt. There is a documented failure mode researchers call overthinking. You hand a reasoning model a simple question, what is 2 plus 2? And if you have cranked the dial to maximum, it can churn through a small essay of second guessing before it answers. You pay for every one of those wasted tokens. You wait longer for the answer. And on an easy question, all that extra deliberation can occasionally talk the model out of a correct first instinct and into a wrong one. So the honest rule is not more thinking is better. The honest rule is, match the thinking to the difficulty. A factual lookup or a formatting task deserves the dial near the bottom. A genuine multi-step proof or a thorny piece of code earns the dial up high. Spending heavy thinking on a trivial question is like hiring a research team to tell you what day it is. It is not just wasteful. Sometimes you get a worse answer slower for more money. And this flips a famous piece of advice completely on its head. Back when models did not reason on their own, the magic trick was to type 4 words into your prompt. Let us think step by step. That nudge alone made older models dramatically better, because you were manually switching on a kind of step-by-step thinking they were capable of, but would not use unless asked. With a true reasoning model, that same advice can backfire. The thinking is already built in, trained deep, switched on by the dial we have been talking about. So when you paste in your own elaborate think step-by-step instructions, or a hand-built script for how to reason, you can get in the model's way, talking over a process that already works and sometimes making the answer worse. The current guidance for reasoning models is almost the opposite of the old wisdom. Keep your prompt clean and direct. State the task clearly. Try it plainly first, what people call zero shot with no scaffolding at all, and add structure only if you genuinely need it. You are not the one doing the reasoning anymore. Your job is to set the task and choose the dial. Then let the model think. Which leaves the deepest question of all, and we have to handle it with real care, because it is one of the most misquoted findings in all of AI. When a reasoning model shows you its chain of thought, that long visible monologue, is that an honest transcript of what actually drove its answer. Researchers ran a beautifully simple test. They slipped a hint into the prompt, sometimes even a wrong one, and confirmed that the hint changed the model's answer. So the hint was clearly being used. Then they read the model's written reasoning and asked one thing. Did it admit in that reasoning that it had used the hint? Often it did not. For one leading model, the written chain of thought mentioned the inserted hint only about a quarter of the time. For another, closer to 2 in 5. Now read that result carefully because the misquote is everywhere. This does not mean the model lies 3/4 of the time, and it absolutely does not mean the model cannot reason. What it means is precise and important. The words it writes out are not a guaranteed, faithful recording of the computation that actually produced the answer. The visible thinking is useful, often genuinely informative, and we should keep reading it. But it is a summary the model writes, not a wiretap on its mind. The real reasoning lives in the activations, the internal math we opened up back in the interpretability episode, and not always in the sentences it prints. Think of the chain of thought as a microscope you point at the model, not a debugger you can step through. And there is a live, public argument about exactly how far this thinking really goes. And the honest thing is to show you both sides, because the science is genuinely not settled. In 2025, one research group ran reasoning models on controlled puzzles whose difficulty they could dial up step by step, and reported something dramatic. Past a certain complexity, the models seemed to collapse, their accuracy falling toward zero, as if they had hit a hard wall of reasoning. The paper was nicknamed The Illusion of Thinking, and the headline took off. See, it is not really reasoning at all. But then came a careful rebuttal. Much of that so-called collapse the critics showed was not a reasoning wall. It was an evaluation artifact. In several cases, the model was simply running out of room, hitting its output token limit mid-solution, or it was being graded on a puzzle that had no valid solution in the first place. Fix the test, and a lot of the cliff disappeared. So where does that leave us? Not that it cannot think, and not that it thinks exactly like we do. It leaves us in the honest middle. These models can do real, verifiable, multi-step reasoning that was science fiction a few years ago, and they also have real limits and failure modes we are still mapping out. That tension between a genuinely powerful tool and a genuinely incomplete understanding of it is not a flaw in the story. It is the frontier. So thinking on demand is not a switch you flip to maximum and forget. It is a dial, sitting on a curve that bends over where every extra notch costs more and buys less. You can spend that thinking two ways, one deep self-correcting chain or many parallel attempts that vote, and the smart move mixes them to fit the difficulty. Push the dial too far and you pay the overthinking tax, more money, more waiting, sometimes a worse answer. And the very advice that once made models smarter, telling them to think step by step, now gets in a reasoning model's way, so you set the task cleanly and let it think. Underneath all of it sits the honest, open question. The thinking it shows you is useful, but it is not always a faithful recording of the thinking it did, and whether these models truly reason or just brilliantly imitate it is a debate the field is still in the middle of. So far this season we have been watching one model think in isolation, but the systems people actually deploy are rarely a single model alone. They are agents, models that remember across a whole task, reach out to tools, and increasingly talk to other models to get something done. And the moment a model can act, not just answer, a new question opens up. How do these agents share what they know, hold onto a memory, and coordinate without descending into chaos? Next time, how agents talk and remember.